Applications of 3D graphics and role of mathematics in graphics. In the digital age, the realm of 3D graphic has become a cornerstone of innovation and creativity, reshaping industries and revolutionizing the way we perceive and interact with the virtual world. From captivating visual effects in the blockbuster movies to immersive virtual environments in video games, the applications of 3D graphics have transcended traditional boundaries, permeating various aspects of our lives and driving advancement across diverse fields. Applications of 3D graphics. The application of 3D graphics are extensive and diverse, spanning across various industries and fields. Here are some notable notes. Entertainment. 3D graphics are widely used in movies, television shows, and video games to create immersive environments, characters, and special effects. Architecture and construction. Architects and designers use 3D graphics to create detailed models of buildings and structures, allowing them to visualize the final product and identify potential issues before construction begins. Engineering and manufacturing. 3D graphics are used in product design, prototyping, and manufacturing processes to create accurate models of components and assemblies. This aids in testing, simulation, and optimization of designs. Medical visualization. 3D graphics are play crucial in medical imaging, allowing healthcare professionals to visualize complex anatomical structures, perform simulations, and plan surgeries with greater precision. Education and training. 3D graphics are used in educational settings to create interactive simulations, virtual laboratories, and training modules across various disciplines, from science and engineering to arts and humanities. Simulation and virtual reality. Industries such as aviation, automotive, and military utilize 3D graphics for simulation purposes, enabling realistic training scenarios and immersive experiences. Advertising and marketing. 3D graphics are used in advertising campaigns to create visually compelling product renders, animations, and visualizations that help promote products and services effectively. Gaming and interactive media. Video game development heavily relies on 3D graphics to create lifelike environments, characters, and interactive elements that enhance gameplay experiences. Virtual prototyping. Companies use 3D graphics to create virtual prototypes of products, allowing them to iterate quickly, gather feedback, and make necessary modifications before physical production. Art and design. Artist designers leverage 3D graphic software to create digital sculptures, animations, and visual effects, pushing the boundaries of creativity and expression. Urban planning and geographic information systems. 3D graphics are used to visualize urban environments, analyze spatial data, and simulate urban development scenarios, aiding city planners and policymakers in decision-making process. Scientific visualization. Researchers use 3D graphics to visualize complex scientific data such as molecular structures, weather patterns, and astronomical phenomena, facilitating analysis and interpretation. These are just few examples, and the applications of 3D graphics continue to expand as technology advances and new industries adopt these tools for various purposes. Role of mathematics in graphics. Mathematics serves as the backbone of computer graphics, providing the essential framework for representing, transforming, and rendering visual elements in digital environments. From geometric primitives to intricate lighting effects, virtually every aspect of graphics relies on mathematical principles for its conceptualization and implementation. Geometry. Geometry lies at the heart of graphics, defining the shapes, positions, and transformations of objects in a virtual space. Concepts such as points, vectors, matrices, and transformations are essential for describing the geometry of objects and scenes. Transformation. Transformations like translation, rotation, scaling, and shearing are fundamental operations in graphics. These transformations are typically represented using matrices and vectors, and mathematical principles like linear algebra are essential for their implementation. Rendering. Rendering involves the process of generating in 2D image from a 3D scene. This process requires knowledge in mathematical technique such as ray tracing, rasterization, shading, and lighting models. Understanding the mathematics behind these techniques is crucial for producing realistic and visually appealing images. Curves and surfaces. Graphics often involves representing complex shapes using curves and surfaces. Mathematical concepts such as Bezier curves, splines, and NURBS or non-uniform rational B-splines are commonly used for defining and manipulating curves and surfaces in graphics applications. 3D mathematics. In three-dimensional graphics, concepts such as perspective, projection, viewing transformation, and depth calculations are essential for creating realistic 3D scenes. Trigonometry and calculus play significant roles in these areas, helping to model the behavior of light and perspective in a virtual environment. Texture mapping. Texture mapping is a technique used to apply images or patterns to surface in a 3D scene. Mathematics is involved in mapping the texture coordinates from the 2D image space to 3D surface space, as well as in performing texture filtering and interpolation. Animation. Animation involves creating the illusion of motion by sequentially displaying a series of images. Mathematics is used to interpolate between keyframes, calculate motion trajectories, and simulate physical phenomena such as collision detection and rigid body dynamics. Mathematics provides the language and tools necessary for expressing and manipulating the visual elements of computer graphics, enabling the creation of immersive and realistic virtual worlds.